Somebody asked the question, going back to continuous data, about how power is affected by variation in the treatment effect. I think it's a very important question. I'm not sure that I addressed it sufficiently in the original video, so I'm going to make up another video that explores this in a little bit more detail. And I'm going to use the example that this person asked about, which was a 4-level study, so I'm going to add levels. He actually was working with the same example that I had, so we have over here districts and schools and classes and students. And let's set an effect size of 0.4, and we need to set the ICCs, even though it's going to turn out that we're going to be blocking at the top levels, or some of them. It's still important to set the ICC. I'm going to use the ICCs that come from an education study, I believe it was in Kentucky, and if I recall correctly, we had an ICC of 0.02 and 0.05 and 0.12 over here. And let's put some costs in. Let's say $4,000 for each district and $2,000 for each school. And with each class within the school is going to be another $500, and each student within the class is going to be $50. And okay, initially this is set up so that it's random at every level, and I can use optimal design and find that it's possible to design a study over here that's going to cost about $250,000 for power of 80%. Now, the question was, how do we deal with variation in the span of effects? And let's say that instead of randomizing districts, we randomize schools, so that now we need to deal with the span of effects at the top level. You'll notice, by the way, that when we do that, we now have the option of making the top level either random or fixed. So first, leaving that at random, we can set the span of effects, and if the overall value for D is 0.4, and we assume that the value for D is going to range over a span, let's say, of 0.3 to 0.5, we can change that until we get 0.3 to 0.5. And you can see what's happened over here. Well, first of all, let me come back for a second. When the span of effects is 0, power is 86%. If I change that so that, and in other words, it's gone from 80% to 86%, right? If I come back over here again and randomize the top, when it was randomized at the top, power was 82%. When I block at the top level, it's gone from 82 to 86%. So it's a modest increase. It's a modest increase in power. The reason that the increase is only modest is because the ICC at the top level had been very small. So when basically what we're doing is we're removing this ICC, this variance in the means, as a factor in power, but the variance in the means had not been that much to begin with, so we're getting only a modest bump in power. If the ICC over here had been larger, we would have gotten a much larger bump. But for the purposes of what I want to do right now, that doesn't really matter. The bottom line is that we have power of 86% with this design. And in fact, if I wanted to get the optimal power for this, first of all, let me add costs. For the blocked district is going to be $4,000. And I click Optimal Design, Compute. Okay, it can't do that because I have no span. I'm going to put in a very modest span over here. Click Optimal Design, click Compute. Okay, and now the cost is going to be about $192,000 to get power of 80%. So now we've established our base study. I'm going to actually bring this back to 0. We have power. You see it makes almost no difference over here. Power is 80%. And by the way, if you hover over that, you'll get the exact value, but it's around 80%, and with no variance in D at the district level. I'm going to increase that now. Let's assume I expect a 20-point variance in D. So instead of 0.40 to 0.40, I'm going to make it 0.30 to 0.50. And power has gone from 86%. I'm sorry, power went from 80% to 79.5%. So in this case, power had only a very trivial, in this case, increasing the variance of D at the district level had only a very minor impact on power. The person that sent the question actually was speaking about TOS square. TOS square, of course, is the variance of D. The reason that we included TOS square as an option, as well as entering the span, is that if the way that you are estimating the variance of D is by looking at a meta-analysis where you're looking at the effect across districts, the meta-analysis is going to give you TOS square, which corresponds to the variance of the effect size across districts. So you actually have the option of entering TOS square directly, in which case you might have had a value of 0.025, and you can enter that here, and the program shows you the corresponding span. It really doesn't matter which one you enter. If you enter one, the program computes the other. I'm going to keep working with the spans because those are a little bit more intuitive to me. Now, what happens if we block at the next level as well? So I'm going to randomize classes, and let's say that we had power was down to about 80%, 79%. As soon as we block schools as well as districts, power immediately jumps to 90%. But in this case, there was no variation in D across schools. Let's put in some variation over there. Let's make that a variation of 20 points. So power's gone from, well, again, it had a very minor impact. In fact, it seems to be affecting this only in, it's almost decimal dust. It went from 91% to 91%. You can see that it's changing in the third and fourth decimals, but not really beyond that. If we add more variation over here, I'm curious myself, if we bring this up to 30 point, which is a fairly wide variation. It means that overall D is 0.4, but it varies from 0.2 in some districts to 0.6 in others. And then we can do the same thing over here. It still is having only a pretty modest impact. Again, this is going to be in part because of the number of blocks that we have. We have 10 blocks at the top level, so any variation in this is going to be divided by 10, and we have 20 blocks over here because it's 2 times 10. So any variation over here is going to be divided by 20, which is part of the reason that this impact is so small. Let me just show you that. If I bring this back over here, let's say, so I have only 2 blocks at the top level and 2 blocks at this level. Okay, well, power, first of all, is down to about 10%. So let me, it's going to be hard to increase the power much without increasing these numbers. But once power at this point is just down low, and there's not much you can do about it without increasing these numbers. Let me go back to the Optimal Design Wizard and click Compute. I have to enter this. This is going to be 2,000 per school. Optimal Design Wizard, and we get a cost of about $90,000. And similarly, we can block this level, so power is now 80%. If I block classes as well, then power jumps to 96%. Again, I can set a span over here, and it has, again, just a pretty small impact. I'm going to make this span 50 points, which means that D goes from 0.15 in some classes to 0.65 in others. That would be in a school where the mean D is 0.4, that D varies from 0.15 to 0.65. And tau square is 0.0156. And when we blocked, power jumped to about 96. In this case, the span is having only a relatively small impact on the power. And again, I can use optimal design. Let me set a cost of $500 per class, and we see that we can get the study done for about $47,000. So I guess what's happening over here is, first of all, it's clear that when you block, at least in this example, we're getting a major, a very good boost in power, so that the study becomes much more cost-effective than randomizing at a higher level, and that holds true even once we take into account the variation in the treatment effect. Now, another question that this person asked was, what happens if we use a fixed effect at the top level? Well, if we do that over here, okay, at this point power was 81%, 82%. If I set this at fixed, okay, well, if I set that at fixed, then we need to increase the number of units. Okay, that seems to be a bug, and I'm going to have to look into that very quickly and fix it. Oh, I see what the problem is. I'm sorry. No, it's not a bug. If we set this as fixed effect at the top level, then what happens is the test is actually done at the second level based on degrees of freedom at the second level. And therefore, we can't have only one unit over here. That was the problem. Okay, so the program is actually doing what it's supposed to and protecting me from my own mistakes. But you can see what happens is that as soon as we set this as fixed at the top level, the power has jumped to 99%. And the reason for that is that basically we removed all of the error at the top level, and with that error removed, power simply jumps up. Now, you cannot use the Optimal Design Wizard when any of these levels is fixed. The whole algorithm simply does not work in that case. But what we can do is just sort of, and we know that we have a minimum of of 2 cases over here, because less than that we won't have enough degrees of freedom. We can try knocking this down to 2 and knock this down to 1, and we get power of about 80%. Or you can manipulate this a little bit, and so you can bring down the number of classes or the number of students and figure out what the most cost-effective design would be. But that's an answer to what happens if you use the fixed effect model at the top level. Let me go back and show you something which I think is very interesting, and I think this might have been part of the question that was being asked. Let me bring these things back to where they were before, so that we have power of about 80%. We've blocked at the top 3 levels. The question had been, I think the person that asked the question was asking for a more intuitive feel of how blocking at these levels and how the dispersion in D at these levels will affect the power. When I first read the question, I read it as also asking a question of trying to understand how the dispersion in D accumulates across levels. Because what we're looking at over here is a span of 50 points for classes within schools, a span of 40 points for schools within districts, and a span of 40 points across districts. But the question might be, if we have this span over here, and this one here, and this one here, or this value of tau square, and this one, what is the span of D across classes, schools, and districts, instead of classes within schools, within districts? Now, this is actually kind of nice. If you click Report and come down over here, let's go to page 4, effect size, page variation in D. Okay, so we have over here the variation. The variation in D was 0.2 to 0.6 for districts, 0.2 to 0.6 for schools within districts. And again, that's an example. That would be in a district where the mean D is 0.4, and then 0.15 to 0.65 for classes within a district where the district, for classes within a school. What we want to do now is get the variation across all of this. If you keep going further and we come to here, let's see, the means, variance, okay. Variation in means within schools, variation in means across. Here we were dealing with variation in means within levels, variation in means across levels. Let's keep going. Variance in the effect size. When we employ blocking at any level, power is affected by the variance in the effect size across clusters at that level. And what we have over here, the variation in effect size within levels is what we were looking at a minute ago. So the variance, the tau square for districts was 0.01, represented a span of 0.4. And the example that we had was a span of 0.2 to 0.6. For schools, tau square was 0.01, span is 0.4. An example would be 0.2 to 0.6. If we come over here, we have the variation in effect across levels. So for districts, it's the same. The tau square is 0.01, the span is 0.4, the example was 0.2 to 0.6. For schools, this is now variation in effect across levels. So if the tau square, if the variance for districts was 0.01 and the variance for schools within a district is 0.01, then the variance for schools across districts is 0.02. And similarly, if the variance for classes within a school was 0.0156, and this is 0.01 and this is 0.01, then the variance for classes across schools and districts is going to be the sum of these, 0.01 plus 0.01 plus 0.0156, which gives us a total of 0.0356. Then we can compute the span that corresponds to that. If the variance is 0.0356, if we take the square root of that, we get the standard deviation. Let me do that quickly. 0.0356. So we have 0.0356. We take the square root of that. The square root of D11 is 0.18868. We multiply that by 4 and we get 0.754, which is the number that you see over here. That's the span. And then, since we know that the mean effect overall was 0.4, we can take 0.4 and we say 0.4 minus standard deviation times 2, and we get 0.4 plus the standard deviation times 2. So we would get, we would expect that the effect size would vary from 0.02 to 0.77, which is exactly what we see over here. Now, again, you cannot simply add up the spans because they're based on the standard deviation. Standard deviations which are not additive, but you can add up the variances which are additive, and then compute the standard deviation of this variance and then the span for that, which is going to be 0.02 to 0.77. So what you're getting over here is a sense that the effect size D, if you're looking at classes across schools, across districts, the effect size D is going to vary from a low of near 0 to a high of 0.77. This might have been implied in the question that the person might have wanted to know, what if we have a sense of how D varies across classes, across schools, across districts, but we don't necessarily know how it varies for classes within schools. This is a way of coming back and checking to make sure that the numbers that you've put in within each level give you the numbers that you're expecting across levels. And then once you have this, you can play with whether you want to assume that most of the variance takes place at this level or at this one or at this one. What we've seen is that in this example, at least, that didn't seem to matter a lot. But you can make sure that the numbers are consistent and that they reflect the expectations that you had. I should mention, by the way, that while blocking at the top level does have a major impact on power, it is not related to to making sure that these spans reflect your expectations. In other words, once we've put in that the span over here is 0.4, that number then carries through to all of the other values as far as we're trying to figure out what the cumulative span of the effect size is going to be. Now, if we say, let me bring this up to 2 again, if we say that this is fixed, then this span has no impact on the power because there's no sampling variation at this level. If we say that it's random, then it does. But whether it's random or fixed, whether or not this value here is having an impact on power, in either case, it still has an impact on figuring out the cumulative span of the effect size, which you can then use to make sure that it's consistent with your expectations. Okay, I hope that I've fully addressed the question. I'm glad that this person asked the question because I think this is an important thing for everybody to understand. But if anybody has additional questions on this, whether the person that asked this originally or anybody else, I would consider it a favor if you let me know about that so I can go ahead and either answer it using text or I'm making another video. I want to make sure that everybody is as clear with this as possible. Oh, one more question. Somebody also asked how this relates to the way that we enter the data in Optimal Design, the other program. The power that's computed matches exactly. The way that they define tau square is a little bit different than the way that we define it, and we were able to set up spreadsheets that, we're very clear about how we define it. I just don't remember exactly how they defined it. There are so many ways of doing this that it's not that our way is better or their way is better. It's just you have to be very clear about what we're doing. We set it up this way because we wanted to make sure that we were being consistent in the way that we define it at each level. If anybody has any questions about they've done an analysis using optimal design and they want to see how the results match this one, if you send me that question, I will get in touch with one of the people that we've been working with who developed optimal design, and she has these spreadsheets which convert from one format to the other. And we can show you that it matches to at least 6 decimal places, or I guess more if you want to display more than that. But this is the way that we've done it, and I hope it's relatively easy to understand. Okay, thank you very much.